I wanted to take center of mass, but there are still some unfinished things which I want to take up. That is, uh, I would say dynamics of circular motion. Dynamics of circular motion. So this is some kind of slightly advanced circular motion than what we have studied. So this is slightly advanced circular motion. Let me first revise our basic circular motion, then I will take you into this. Then we will see some very interesting class of problems. Very interesting class of problems. So first I told you long back about uniform circular motion. Uniform circular motion where speed is constant. So in this circular motion, speed is constant. Velocity is changing anyway because direction is changing. So velocity is changing as direction is changing in circular motion. Then we also saw in uniform circular motion, because velocity is changing, it means actually there is an acceleration. So originally I would put it like this: there is a force which causes acceleration, which is causing this velocity to change in direction. This acceleration, if we calculate, it comes out to be v square by r. This was the acceleration and it is directed towards center. We can do some interesting derivation here using a different idea. I have a circle. This is my x-axis and this is my y-axis. So if the particle was here at t equal to 0, at t equal to t seconds, it would have traveled a distance vt, and the angle it would have covered is vt by r. Vt by r. So angle is arc length by radius. Radius is r. So the particle is here now. This is its position vector. Okay. I can split it into two parts. So I can write the position vector as r cos vt by ri plus r sin vt by rj. If you differentiate this, you get velocity is minus v. So r is a constant. Cos derivative is minus sin vt by r, and derivative of vt by r is v by r. So when v by r comes, r gets cancelled. So minus v sin vt by ri plus v cos vt by rj. I got it by differentiating it with respect to time. You could have done in a different way. If this is the velocity, this angle is also vt by r. So this angle is pi by 2 minus vt by r. So you can take components of that velocity. X component will be cos pi by 2 minus vt by r, that is sin vt by r, directed along negative x-axis. Okay, and similarly y component I could have got from there. If you further differentiate this, you get acceleration as minus v square by r cos vt by ri. I am differentiating again with respect to time. Minus v square by r sin vt by rj. If you take minus v square by r out, cos vt by ri plus sin vt by rj is unit vector in the direction of r, because if you divide this r with its magnitude, which is r itself, capital R, so you get unit vector r. That's exactly the acceleration directed towards minus r cap. If this is r cap, okay, unit vector in the direction, minus r is directed towards center. So this is another way of deriving this uniform circular motion acceleration. So main point I want to tell you is acceleration in uniform circular motion is v square by r directed towards center. This was the thing which we derived long back. If it is non-uniform circular motion, in addition to v square by r, which is the radial acceleration directed towards center, there is also a tangential acceleration, which I said is derivative of speed with respect to time. This is what I said. Now, in today's class, what we are going to do is, I am going to introduce you to the angular variables in circular motion. So we shall introduce angular variables in circular motion. Sometimes it is very convenient to deal with angular variables. Up till now, I have not talked about angular variables in circular motion. We already did in kinematics using these two ideas. V square by r is radial and dv by dt is tangential and all that. But now we are going to introduce the angular variables. So let's see how we define them. So we are defining these angular variables in the context of circular motion. So there is a object going in a circle. So this is the center of the circle, and originally the object was here at t equal to 0, radius is r. I'll call this P, point P. So the object is going in anti-clockwise direction. Now this OP, I can call it radius vector of the particle which is moving in circle. The radius vector of particle moving in circle. So when the particle comes here, the radius vector just 1 minute. So when the particle is here at P dash, the radius vector will be this, OP dash. So this radius vector is rotating as the particle moves in circle. The radius vector rotates as particle moves in circle. Just 1 minute. Okay. So radius vector rotates as particle moves in circle. Now, so what I am saying is the angle swept by radius vector is called angular displacement theta. Angular displacement theta. So you see this angle, whatever is swept by the radius vector, that is called angular displacement theta. Now, so I am for the first time introducing angular variables, everything related to angle. I can always say the arc length, that is the distance covered by the particle. See, the particle came from here to here. It covered some distance. The distance covered by the particle, I can say it is r into theta. This is the standard definition of angle in radians. How do you define angle in radians? It is defined as arc length by radius. That's the definition of angle. Whenever you have two lines, somebody asked you what is this angle. Take a compass and cut a length. Get the arc length, get the radius, take ratio, that gives you angle. Now if you take a bigger radius, you get a bigger arc, but ratio is going to remain same. Ratio is going to remain same. So in that sense, from that definition, you get this. Now, as the particle goes in circle, the speed with which it covers this angle, there is some speed with which it covers this angle. That speed, we call it as angular speed. The rate of change of theta. Theta is our angular displacement. Is called angular speed. So I can say d theta by dt. This is called angular speed, and we give a new symbol for it. It is denoted by omega. Angular speed is given by omega. This is the symbol we use for angular speed. Means how fast this particle is covering this angle. That is what that information is being given by omega. Suppose you see the particle is going like this. The angular speed is less. Suppose the particle goes like this, very fast. The angular speed is more. So how fast the angle is changing, that is the angular speed. Now I can go one step further and say angular speed itself could be variable. So rate of change of angular speed itself is called angular acceleration, denoted by alpha. Angular acceleration denoted by alpha. So let me once again put these things in perspective. Angle covered by the particle is the angular displacement. You can also define it as angle swept by the radius vector. What is radius vector? Line joining center of circle to the particle is radius vector. Whatever angle the radius vector sweeps, that is angular displacement. Now how fast it sweeps, that is angular speed. Rate of change of angular displacement is angular speed. If the radius vector is sweeping angle very quickly, then angular speed is more. The radius vector is sweeping angle slowly, angular speed is less. So this angular speed may be constant or it itself may change. For example, when you switch on a fan, the fan's angular speed is increasing. From 0, it is increasing to its maximum value. So during that phase, there is angular acceleration. But once it reaches a constant angular speed, beyond that the fan's speed will not increase. It is constant. That is when there is no angular acceleration. So the moment you switch on the fan, angular speed is increasing. There is angular acceleration, and after certain time, the angular speed of the fan is now constant. Then there is no angular acceleration. So, for example, I'll show you with some, movement. So I start from here. First I am going slowly, then I am speeding up, then I am speeding up and going more and more speed. There is an angular acceleration. Whereas if I am going with the same angular speed, there is no angular acceleration. So this is the idea. So we have got now in the lines of kinematics, we have got angular kinematics. So what is angular kinematics? Omega is d theta by dt and alpha is d omega by dt. These are our basic definitions of angular kinematics. For example, I have got similar idea in kinematics. Though there we have defined vector quantities, here right now I am defining all things as scalars. My omega is scalar, my alpha is scalar, my theta is definitely scalar. Later we will see how to treat omega and alpha as vectors. Okay, there are some quantities which you can treat as vectors. You give a direction to them. They inherently don't have any direction of their own. but you give direction to them and you can treat them as vectors. Why you want to do that? So that certain section of physics becomes easier, particularly when we go to rotational dynamics. There it is very convenient to treat omega and alpha as vectors. But as of now, omega and alpha are scalars. So I will write here can be treated as vectors. But as of now, they are scalars. Theta cannot be a vector. Theta cannot be a vector. I see some people writing theta equal to omega naught t plus half alpha t square for constant alpha. Just like, for constant acceleration, you have s equal to ut plus half t square. Some people write this is fine. The problem is they keep an arrow like this. No, this is where I have serious objection. This cannot be a vector. Okay, we will see why theta cannot be a vector. Because theta doesn't follow this rule. Theta 1 plus theta 2 is not equal to theta 2 plus theta 1 in 3D. I'm not talking about 2D. Okay, any vector quantity should obey this law. For example, a plus b should be b plus a for any vector quantity. For example, you went 3 meters east, 4 meters north. Suppose you reverse these displacements. You went 4 meter north and then 3 meter east. In both cases, the displacement is going to be same, right? 5 meters starting from initial to final. Whichever way you go, you can reverse the order of adding these vector quantities. But surprisingly for theta, it doesn't follow this rule. Theta 1 plus theta 2 not equal to theta 2 plus theta 1. You might be saying, sir, I have a line, I rotate by 30, then I rotate by 60, and it came perpendicular. Suppose first I rotate by 60, then I rotate by 30, it again came to same position. So why is theta not a vector? Now the answer is I am not talking about 2D. In 2D it might work, but let's talk about 3D. Let's go one step further and talk about these angles or angular displacement in 3D. Suppose I have a book on the table like this. Okay, this is a book. Let us say it says Concepts of Physics. The book name is Concepts of Physics. Author is somebody. Okay. Now, suppose I take this as y-axis, this as x-axis, and this as z-axis. So the book is lying in xy plane and z-axis is perpendicular to the book. Now, what I'll do, first I will rotate the book about x-axis by staying on positive x-axis and looking towards origin. By staying on positive x-axis and looking towards origin counterclockwise by 90. So I rotate book about x-axis. How am I rotating about x-axis? So I am staying on x-axis. I am staying on positive x-axis, looking towards origin, and I assume x-axis like a rod passing through the book, and I rotate the book by 90 degree counterclockwise, anti-clockwise. First I will do this rotation, then I do the same kind of rotation about y-axis. I stay on positive y-axis, I look towards origin and rotate the book 90 degrees about y-axis. So let's do this. First, if I rotate about x-axis, so you are staying here, looking towards origin and rotating the book by 90 degrees anti-clockwise about x-axis. So you are rotating. So if you do that rotation, how you will see? You will see the book coming to xz plane in this manner, concept of physics will be visible right now like this, concept of physics. Then where is the y-axis? It is like that. So the book you rotated, okay, it came to standing position. Now you rotated it about x-axis. Now you stand on y-axis there, look towards origin and rotate the book 90 degrees counterclockwise, okay, as you see towards origin. So how would that be? Then I think the book will come to this position. If you imagine it, if you stand here and as you see you are rotating anti-clockwise. So for us it will be clockwise. For us it will be clockwise. For him, somebody standing on y-axis, positive y-axis, it will be anti-clockwise. Because when somebody is rotating anti-clockwise and you see from opposite direction, it will be clockwise. So right now for us, we are on negative x-axis, so rotated clockwise. So concept of physics, C appears like this, N appears like this. Okay, whatever. The book is coming to this position. Now I will reverse these rotations. First I rotated the book about x-axis by staying on positive x-axis and looking towards origin. I rotated it by 90 degree anti-clockwise. Then I did the same thing about y-axis. If you reverse the rotation, suppose first you rotate the book about y-axis, okay, so for us it will be clockwise rotation. So this part, whatever you are seeing, when you rotate it about y-axis, that part will become vertical, okay, and the book comes to this position with C, O, N, something like this. That is my y-axis, this is my x, and this is my z. So the book came to this position. The shaded part of the book, whatever I shaded, you can see that. So for us, I rotate the book by clockwise, but actually the person standing on y-axis, positive y-axis, for him it is anti-clockwise. How is he rotating about y-axis? Think y-axis as a rod passing through book, okay, and you are as a hinge passing through the book, and you are rotating about the hinge. Whenever I say rotate about x-axis, imagine a hinge passing through x-axis. The book is attached to the hinge and you have to rotate. Similarly, when I say rotate about y-axis, imagine a hinge passing through y-axis and rotate about it. So now I rotated about y-axis first, then I stand here and rotate about x-axis anti-clockwise. This portion which is there now that will stand and come like this. So when you rotated first about y, then about x, I am seeing this position of the book. But when you rotated first about x, then about y, you are seeing this position of the book. So the final position in both cases is not same. That means when you give two angular displacements to a body, okay, in 3D, the final outcome is not same. When you give two linear displacements to a body, first about x, then about y, or first about y, then about x, the final displacement is same, linear displacement. But the body is coming to the same position. But when you talk about angular displacement, when you are rotating, if you first rotate about x-axis and then about y-axis, in the second case you first rotate about y-axis and then about x-axis, the final position of book in both cases is not going to be same. So I am claiming that theta 1 plus theta 2 is not theta 2 plus theta 1. If it doesn't follow this rule, which we call as commutative rule of vector addition, then it is not a vector. Every vector or vector quantity must obey this rule of vectors. But theta does not obey the rule of vectors. So it cannot be a vector. So the problem is you can't write theta as a vector. However, d theta, very small tending to zero angular displacement, can be treated as a vector. So you put an arrow on this d theta like this, you can treat it as vector. It's not a vector, but you can treat it. Now again, look here. You cannot write d theta bar. This is wrong. Theta bar itself is wrong. How did I write it? D theta whole bar. You see, even the way how you write is very important. There is a difference between d of theta bar, this is wrong, d theta whole bar, this is fine. You're treating d theta as a whole as a vector. So that distinction matters here, even how you are writing. So bottom line, in angular kinematics, when we take the angular variables, theta, alpha, omega, we are still treating them as scalars. They are scalars. Later, when we go to rotation, omega and alpha can be treated as vector. Even d theta can be treated as vector. Theta cannot be a vector. So my ideas are now, theta can never be vector quantity, can never be vector quantity. Okay, even vector and vector quantity, they are different. Vector is a mathematical object, vector quantity is a physics thing which follows the rules of vector algebra. Anyway, theta can never be vector quantity. D theta can be treated as vector, can be treated as vector quantity. What about omega, alpha? Again, they are scalars, but they can be treated as vector quantities. Then what will be the direction of these if you are treating them as vector quantities? Generally, we give this direction based on right hand rule. Suppose if you are rotating, a point is rotating by a small angle d theta anti-clockwise, you take right hand and curl your fingers anti-clockwise, thumb gives the direction of omega. So in this case, the omega is out of the screen, out of the screen. Suppose if you rotate this line by a small angle, I shouldn't say small, infinitely small angle d theta, I can treat it as a vector, the direction is out of the screen. Similarly, if there is a something which is rotating anti-clockwise, I can treat omega as a vector and it's out of the screen. Okay, same goes for alpha, depending on how alpha is. So d theta, omega and alpha can be treated as vectors, nothing wrong. But right now we are treating everything as a scalar. So our definitions are just in the line of kinematics. D theta by dt is omega, that's one definition. And d omega by dt is alpha, that's another definition. So these two will help us to solve any kind of angular kinematics. These two help us solve any kind of angular kinematics. Okay, any problem in angular kinematics, we can solve using them. By dividing them, there is also a third definition. Alpha is omega d omega by d theta, something like a equal to v dv by dx, right? We have this also. Now, most of the times we have a special case, just like in kinematics, which is alpha is constant. We get this special case most of the times. You can also get cases where alpha is a variable, but if you find alpha is a constant, then you can integrate this. So d omega is alpha dt, and when you integrate from 0 to t and omega naught to omega, alpha is a constant, pull it out. So you get omega minus omega naught is alpha t, or omega is omega naught plus alpha t. Again, you write this omega as d theta by dt and integrate. You get theta is omega naught t plus half alpha t square, just like kinematics. So we have similarly 5 equations here. Let me write them. If alpha is constant, we have the equations of motion here. Omega is omega naught plus alpha t. Theta is omega naught t plus half alpha t square. Omega square minus omega naught square is 2 alpha theta. Theta is omega t minus half alpha t square. This is like s equal to vt minus half a t square. And theta is omega plus omega naught by 2 into t. You have 5 equations, but all these are scalar equations. There is no vector equation here. In kinematics, except one, which is v square minus u square is 2 a dot s, others were vector equations, right? We could write components of them, but here there is nothing of that sort. All are scalar equations. That's the difference between the angular kinematics and linear kinematics. For example, in linear kinematics, if I write a equal to constant, most of these are vector equations. V is u plus at, except the one where you have v square minus u square is 2 a dot s. That actually goes into work energy. Anyway, I'm just writing here s equal to ut plus half at square. Then you have s is v plus u by 2 into t. V plus u by 2 is average velocity if if a is constant. If a is not constant, you can't say average velocity is v plus u by 2. You have to do integration. Average of a quantity, we saw that. The quantity integrated over time by time interval. Anyway, so S equal to Vt minus half At square. Very powerful formula which many people don't know. Useful sometimes in very weird cases. Like ball thrown up at highest point V is 0. We can use this. I don't know you, but suppose time is given, A is given, I can find S by putting V0. Very interesting. And V square minus U square is 2A dot S. We saw this. This is the only scalar equation here which actually has some interesting relation to work energy. Now that we have learned work energy, when is this equation applicable? For constant acceleration, right? So if I multiply with half m v square minus u square is half m a dot s, half m into 2 a dot s. I'm multiplying by half m on both sides. Half and 2 get cancelled. Ma is f. F dot s is work done by all forces provided they are all constant. Net force. It's a constant force you can write. So it's work energy theorem actually. V square minus u square is 2 a dot s is actually an equation which connects you to work energy theorem for constant net force. Okay, we have derived work energy theorem in a more general way. If you go back to my lecture on work energy, in a more general way, we have derived the work energy theorem. But this is one way to derive it, assuming the total force on the object is constant. Okay, so similar equations are there in our angular motion also, angular variables, but they are all scalars. Now, there are problems where you use these equations to solve some problems. I am really not very interested in them right now. The more interesting topic for me, there are many problems in angular kinematics also. You can take any standard book and you'll be getting some good, solve some 10 questions and done, not more than that. But let's go to the more interesting case of relation between linear and angular quantities. Let's look at this. Relation between linear, this is a more important topic for us, and angular quantities. So when the particle is going in a circle of radius r, suppose the particle was here at t equal to 0, and after some time at t equal to t, let us say it covered an angle theta and distance l. So I can relate L is r theta provided theta is in radians. So the relation between linear and angular is the linear distance traveled by the particle is r times the angular displacement. I don't generally call it angular distance, but you can say angular displacement, angle swept by the radius vector. Then you differentiate this equation with respect to time. You get dl by dt, rate of change of distance traveled, r is a constant, is d theta by dt. We know rate of change of distance traveled is speed. There is also another definition for speed, magnitude of velocity. Whether you say rate of change of distance traveled or magnitude of velocity, both are same, no difference. Is r into d theta by dt is, of course, just now we saw it is angular speed omega. So this is another important relation between linear and angular quantity. Okay, v is r omega. When a body is going in a circle, the speed at any moment is given by r into the angular speed at that moment. So most of the times, linear quantities are into angular. Look at this rule. Linear, most of the times. I'm not saying always. Most of the time. There is one exception. We'll look into that. Linear is radius multiplied by angular. For example, linear distance traveled L is radius into angular displacement theta. Differentiate, linear speed is radius into angular speed. Further differentiate, now is the critical point. V is equal to r omega. I am differentiating with respect to time. So I have dv by dt is r is a constant, d omega by dt is alpha. My question to you, what is dv by dt? Think and tell me carefully. Don't be hurry. Don't be in a hurry. What is dv by dt? Can we call it acceleration?
Yes, sir.
No. D velocity by dt is acceleration. And unfortunately, you cannot even call it magnitude of acceleration, because if you take mod like this, so magnitude of acceleration would have been mod dv by dt, but this may not be equal to d of mod v by dt. This is a very specific thing. I think we did this long back in circular motion. This is rate of change of speed. It is tangential acceleration. It's not total acceleration at all. This is where people need to be very thorough with concepts. Many people miss this. They feel dv by dt is acceleration, or they'll say magnitude of acceleration. No. First of all, I want to claim mod of dv bar and d of mod v bar, these are not equal. We saw, I think, this. For example, a body was going with 3 meters per second along x-axis, and suddenly it took, suppose, this is my coordinate system, x-axis, y-axis. Okay, a body was going with 3 meters per second, and along x-axis it took turn without changing speed. Now let's look at this. dv, if you find it here in this case, change in velocity, final minus initial, and then there is mod of that. Whereas d of mod v, that means change in magnitude of velocity, change in speed is, these are clearly not equal. This is giving you change in speed. D of means differential of mod v means speed. A very in a very small time change in speed. Speed is not changing, it is always 3 just to get up. So this is giving you 0, whereas mod dv, that is giving you 3 root 2. So both are not same. That's why we have to be very careful. Mod of dv by dt is magnitude of acceleration. d by dt of mod v, d by dt of speed, is tangential acceleration. You see that? It's not even total. It's just a, you are differentiating only speed. You did not even care to look at direction. So it doesn't give total acceleration. It gives you only tangential. So I get from here, tangential acceleration is r alpha. So I got L equal to r theta was my first linear angular relationship. Then when you differentiated it, you got speed is r into omega. Then when you differentiate, you get a tangential, not total, is r into alpha. Look at this. This is the problem with linear and angular. When you come to acceleration, r alpha is only tangential. It is not even total. Now there is another component of acceleration which is radial, which we already saw at the beginning of lecture as v square by r. How can we write it in terms of angular variables? Now v we already saw is r omega. So r square omega square by r. So it is omega square r. You see that? Sorry. You see that? So radial acceleration, till now we learned it as v square by r, long back in kinematics. Okay. Now I am introducing the angular aspect of it. Same v square by r, you can write it as omega square r here. It is directed towards center of the circle in which particle is moving. So we have got 4 relations now. Okay. In 3 relations, it is straightforward in a sense that linear quantity is radius into angular. Linear is radius into angular. Linear, which of course is tangential here, is radius into angular. This is the only case where you got omega square r. Okay, omega square as such uh, doesn't give any physical value for angular, but when you multiply with r, it becomes the radial acceleration. So these are the 4 important relations which we need to be very thorough with when we go further, and particularly when we go to rotation, When we go to plane motion and fixed axis rotation and things like that, all these will again come back. So if we are not thorough now, they will haunt us. That's the problem. Anything that you are not thorough in the whole mechanics, whatever we discussed, it will haunt us in rotation. Because rotation requires calculus, rotation requires vectors, rotation requires kinematics, rotation requires circular motion, rotation requires Newton's laws, rotation requires friction, rotation requires work energy, rotation requires center of mass and collisions, which we are going to discuss next. This chapter called rotation is a nightmare. It is amalgam of all these concepts put together and much more. That's what makes it tough. So we have to be very thorough with all these before we can attack it. Conversely, the one who can attack rotation will obviously know all these things very thorough. It's also that way. So anyway, so this is our relationship between linear and angular. Very important relations. We need them. We definitely need them. What is the advantage of doing things in angular? You see, suppose, look at this very interesting example. Suppose this is the center and I have a rod here. Let us say a rod. Okay, this is a rod. There is one particle here at a distance r1. Okay, there is another particle here at a distance. So this is r2. And let's say this is r1. So let me write it like this. And this rod is rotating. So rod is basically now some kind of, like we saw in our previous case, the radius vector. If you remember, I told you here, the radius vector were here, which is line joining center to the particle. So here the rod is looking like a radius vector, but there are two particles here. One particle is here, I'll call it P1, and other particle here P2. There are two particles, and as the rod rotates, the radius vector rotates, these particles are also going in circles. So this particle is going in circle, this particle is going in circle. Now you see, after some time the rod would have come to this position, somewhere here like this. Okay, my diagram is not very perfect. Let me see if I can draw it a bit more authoritatively. Okay, so this particle P1 came here, it went in a circle. Particle P2 also came there, it went in a circle. Now you see, both these particles traveled different distances. One traveled L1 and one traveled L2. In the same time they traveled these distances. So obviously their speeds also should be different, because you know the second particle traveled greater distance in same time. Okay, suppose if you take this position as t equal to 0 and this position as some t equal to t. In t seconds, first particle traveled only lesser distance, L1. So it traveled slowly. Second particle traveled greater distance in the same time. So it traveled fast. Naturally, whoever travels more distance is faster. You and I going a bike, separate bikes. In 1 hour, you traveled only 20 kilometers, I traveled 80 kilometers, I am the fastest. So, if you see the linear variables, in the same time, distance traveled is different and speed was different. But if you look from angular perspective here, both covered an angle theta only. See the beauty of this. And both have got same angular speed because they covered the same angle in the same time. So omega is same for both and theta is same for both. So sometimes, the linear variables may be different, that kinematics may be a bit more complicated, but suddenly when you look at it from angular variable perspective, the problem may look easier because both are traveling same angular displacement and both are covering same angular displacement and in the same time, so both have got same angular speed and so on. Particularly when we go to rotation, this idea is very useful. The body is rotating, fixed axis rotation or whatever. This is the fixed axis rotation. The rod is rotating about an axis punched into the screen here at so-called center. The rod is rotating about that axis. So the angular variables are same for all particles of the body. That gives an advantage. We can easily deal with the angular kinematics first and later get to the linear kinematics. So once you got the angular speed of the rod, how do you get linear speed? Multiply by corresponding radii. This has a smaller radius, so lesser speed. This has a greater radius, so it has a greater speed. So there is an advantage of dealing with angular quantities. Sometimes linear quantities may be different. The angular quantities could be same. That's why we are looking at this chapter. It's sometimes very convenient to deal with things in terms of angular variables. It's easy to visualize. Okay, though both travel different distances here. You see the angle subtended is same, so they covered the same angle. This particle covered theta. This particle also covered theta. So that's the advantage, the distinct advantage we have here. Sometimes angular variables are same, so it makes our life easier. First you calculate all the angular quantities, then you convert them into linear if required. That's what is the idea here. So this is as far as relationship between linear and angular is concerned. Now, how is this useful in our applications? So let's look at it. So first I am looking at some applications where we have got Newton's laws only, no work energy ideas. There is one thing called conical pendulum. Let's first look at this. Conical pendulum, very interesting application where you have got a string and a stone. Oops. Okay, and then you try to rotate it as a cone. How? It will go in a circle like this. Okay, you hold a string sometimes and try to rotate it, right? Like that kind of thing. Okay, so basically it's going with some angular speed omega in a circle. The stone is going in a circle of some radius. Length of the string is given to us. Okay, with angular speed omega. Now I want to do some analysis. The mass of the stone is m. I want to find the angle it makes. If you are rotating with omega, I want to find this angle. What is the angle it makes with vertical? So what is given? Given to me omega, length of the string, and mass of that object which is tied at the end of the string. Find theta. This is what is my question. So depending on what angular speed you are rotating, the angle made by string with vertical can change. Okay, so we'll try to find it out. Now, what is a free body diagram? Let's draw the free body diagram of this object. There is tension like that. Then there is mg, and I am in ground frame. I am a ground frame observer. I am applying Newton's laws from ground frame, and ground is approximately, Earth is approximately inertial. For all phenomena on Earth, Earth is inertial. For all celestial phenomena, Earth is non-inertial. Now, we are doing this experiment on Earth, so we are an inertial observer. So there is tension, there is mg, and it's going in a circle, so there is an acceleration towards center, which is omega square r. What is the radius here? If you say this angle is theta, it is L sine theta. Look at that. The radius is L sine theta. Very important technical detail. L is given. We are trying to find theta. Radius is L sine theta. Now, how do we apply Newton's laws? So, whenever a body goes in a circle, it is best to apply Newton's laws in the radial, tangential, and perpendicular to the plane of circle. Here, radial, I can split t into parts. This is also theta. So, in the vertical direction, t cos theta is mg. Because vertically the stone is not moving. It is at the same level, right? It's not going up and coming down, something like that. It's at the same level and rotating in a circle. So vertical force is balanced, t cos theta is mg. And horizontally, t sin theta is the force which is acting towards center, which in our case is the centripetal force. The tensions component is the centripetal force. Centripetal force doesn't mean a new kind of force. It should be tension, friction, mg, some real force. Some people say, I asked them a question, what force is making it go in a circle? This is centripetal. It's an idiotic answer because they are indirectly saying it is towards center. I already know that. I am saying what force makes it go in a circle. You are saying, sir, a force towards center of circle. Centripetal is another name for that. I am asking what force. You are saying force towards center. I am asking what is that force. It's like, you drop a stone. I ask what force is making the stone come down? Downward force, sir. As if it's a new elevation. I'm asking why it is coming down. Gravity. Similarly, here the centripetal is tension. So T sine theta is mass into acceleration, which is omega square L sine theta. Why is acceleration omega square L sine theta? You go back. Acceleration is omega square R radial. Now I am using angular variables, right? So I wrote omega square R here is L sine theta, and this gets cancelled, sine theta. So I got tension as m omega square L. You take this tension and put it here, you will get the angle. Because you want, after all, the angle, find theta, right? Here theta got cancelled, but there is theta in that equation. So we'll put T as m omega square L here. So m omega square L cos theta is going to be mg. So my cos theta should be g by omega square L. This is the angle. That, so you can find the angle from here. But there is a problem with this. Let me tell you what is the problem. Your cos theta can always lie only between -1 and 1. It cannot go beyond that. Forget about negative values. Let's look at the positive values. Okay. Forget about the negative values of cos theta. So I can say g by omega square L should be less than or equal to 1, or my omega square should be greater than or equal to g by L, or my omega should be greater than root g by L. Only then this will go in a circle with making some angle. Only then the stone will go in a circle making some angle like this. What if omega is less than root g by L? The problem is it cannot stay there. It will come down. It will be in a vertical position. Why like that? Let's understand this a bit more deeply. See, it should be in equilibrium vertically. That means the tension should have certain particular value. The vertical component of tension should have certain particular value, and simultaneously the horizontal should be able to provide the centripetal force omega square L sine theta. Okay. So for that, if the omega is more, the tension is more, and its vertical component can balance mg. Suppose omega is less, then tension is less. Then tension says, boss, my vertical component cannot balance mg. I cannot hold you, so it will start coming down. You see this logic. Once again, let me go back to the equations. You got T equal to m omega square L. Only if omega is more, then I can hope part of T, that is T cos theta, can balance mg. If T is less, if T is only less than mg, part of T can balance mg. Bullshit. T is only less than mg. Then T cos theta, which is even less, how can it balance mg? So there is a minimum omega for this. So you have to, if you try, hold a stone with a string and try to give a small angular speed, it will stay there. Big, then it will go in a circle. So you have to give that sufficient omega. Okay, so in all these cases, in these kind of problems, what we are doing, when something goes in a circle, we are applying the radial force is mass into omega square r. V square by r also correct, but because we are in angular variables, we are applying omega square r here. These are the kind of applications we have. So this is called a conical pendulum. Why it is called a conical pendulum? Because this ball is sweeping a cone, right, with some semi-vertical angle theta. If length is L, radius is L sine theta. So you are giving the appropriate omega so that it is sweeping out a cone. So it's called a conical pendulum. What is a pendulum actually? Any object generally which is suspended except about its center of mass is called pendulum. We will see later when we go to simple harmonic motion. Different kinds of pendulum, physical pendulum, simple pendulum. Okay, simple pendulum. Where is the center of mass of the bob? Here. Where is the point of suspension? Here. So point of suspension should be different from center of mass. Suppose you take a rod. Where is center of mass? Here. We'll see later what is center of mass. If you hold it here and give a small displacement, it will oscillate. Tick, 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 tick. But if you hold it here at the center, it won't oscillate. See, look here. I have this marker. I hold it at top point. Its center of mass is somewhere here. I am not holding at center of mass. So if I give a small thing, it will oscillate. But if you hold it at center of mass, you give something, it won't oscillate. It will just happen. So pendulum is any object which is suspended except about center of mass. Right now, center of mass is some kind of geometric center. Once when we go to that topic, we will see. So this is called a conical pendulum because it's sweeping out a cone while oscillating. So it's called a conical pendulum. Or you can say in simple words, pendulum is any object which can oscillate. That's a pendulum. Okay, any object which can oscillate. Tick, 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 tick. We have pendulum clocks. So any object which can oscillate, we can call it a pendulum. So this is called a conical pendulum. Let me tell you, there is another interesting application. It's called a death well. In death well, very interesting application. You have a cylindrical room. You have a cylindrical room like this. Okay. And you go and stand on the floor of the room and touching the edge of the wall of the cylinder and just stand there. Then what happens? The cylinder starts rotating slowly with angular velocity omega at certain angular speed. Once it reaches the desired angular speed, you are rotating in the cylinder along with the cylinder. Once you reach the necessary angular speed, this base of the cylinder is removed and you will just be sticking to the wall and hanging there. You won't fall down. Okay, after sufficient omega is reached, the base will be removed and you will just be hanging to the wall. Why you are hanging to the wall? So let's analyze this. First of all, after I remove the base, let me try to draw the free body diagram. There is a normal force acting on you. Otherwise, why will you be going in a circular path like this? Without any force towards center, how you will go in circular path? You cannot. So here there is a normal force by the wall of the cylinder, because of which only you are going in a circular path with omega. So your acceleration towards center is omega square r, where r is the radius of the cylinder. So I can write n equal to m omega square r. So more the omega, more n. So they will first rotate the cylinder to sufficient omega so that the normal force on you by the cylinder reaches a particular value, a good value. Okay. What is the critical case where you are just ready to fall down? You are still not falling down. You are just ready to fall down. What is happening there? There is mg on you, and that is just being balanced by limiting friction mu n. Okay. So first n should reach a good value. Then that mu n can balance mg. If n reaches a poor value, where mu n cannot balance mg, you will slide down. You will fall in the death well. Gone case, death. So critical case, critical omega is where you reach just that particular n so that mu s n can balance mg. So mu s n is equal to mg, where that n is given by m omega square r. So I'm going to put in there mu s m omega square r is mg. So you got that critical omega is g by r mu s under root. Even better is that omega should be more than that. Then you are safe. You will be sticking to the wall. You cannot go down because the friction on your back is preventing you from going down. You are stuck to the wall. Of course, the wall should not be very rough. Otherwise, our back will get scars, right? So if you wear a thick shirt, maybe a coat, so that the friction by the wall on your back is holding you from not going down. It's called death well. Very interesting application. We can make a play area. The children will be given coat. They will be asked to go into this room. Then the room will start rotating, and suddenly base is removed. They will all be screaming, ah! So that kind of application is there. So we will look at a couple of more applications in our next class, and then we will see certain strange ideas roads are banked, they are inclined so that you can take a sharp turn at high speed. Railway tracks are banked. Banking of roads is one another application. I taught you today the conical pendulum, the death well. Banking of roads is a very serious application. Along with that, we'll see a couple of problems. Then I'll talk about centrifugal force, which is a pseudo force. It doesn't come in ground frame. So sometimes people talk about this centrifugal force. Actually, it's a pseudo force. Centrifugal is a pseudo force. Centripetal is because of some tension, normal, whatever, towards center. Centrifugal is there, another term. It is away from center. It doesn't come in ground frame analysis. If somebody says in ground frame centrifugal, he doesn't know physics. Centrifugal is a non-inertial. We'll talk about it in next class. So our next class will be dealing with those ideas. So any doubts in this? Is it okay?
No, sir, no.
Cool. So I'll close it here. I'll send you these files. Okay. Inshallah. Bye. Huh?